All right, let's take a look at what simplifying radical expressions is all about in lesson 0.4. We're going to be expanding your ideas of what square roots are. We're going to go into cube roots and fourth roots, and they call those the nth roots. So simplifying radicals, they're going to be expressions that have radicals in them. We can change the index of these things. So let's jump into some vocabulary here right away, and that's what they describe down a little bit further. But this number that you put right in here is called the index. The index tells you what root you want. Inside the radical is called the radicand. So the radicand is the number we're going to find the root of. So here's some examples of what we've done prior to. We've been very comfortable with this concept of the square root of, say, 9. The square root of 9 technically is plus or minus a 3. Because we can take, and here's our reason behind this, when we take the square root of 9 and we don't put the index 2 in there, if you don't see when it's already implied that it's a 2, we're looking for a number that we can square to get 9. And that's why we got 3. So 3 is said to be the square root of 9. And that's what they're saying, that a number happens to be the nth root of another number. So 3 is the square root of 9. We're going to jump into some other ideas where it's not always going to be the square root. We're going to be using ideas of cube roots. So we're going to change that index from a 2 to a 3. Well, some easier examples of the cube root would be the cube root of 8. In essence, we're looking for some number we can cube to get 8. So what is a number that we can cube to get 8? So that means I have to find a number such as 2 times 2 times 2, which is 8. So 2 is the nth root of 8. So 2 is the cube root of 8. So that's kind of what the terminology and what they're talking about here in this opening paragraph. Okay, so now let's take a look at their key concept, nth root of a number. So a and b are real numbers. We've talked about what real numbers are, and let n be any positive integer greater than 1. So our index, n, is what they're talking about. Our index is going to be a positive integer greater than 1. Can't be fractions, can't be decimals, things like that. Then if a equals b to the n, then b is the nth root of a, which is what I was just demonstrating to you. If I have b to the nth equals a, that's the same thing as saying 2 to the third equals 8. Then they're actually telling us that this 2 is the cube root of 8. So 2 is the cube root of this 8. That's that terminology they're getting across there. This next part, it says if a has an nth root, so if there is an nth root, the principal nth root, that's an important concept, the principal nth root of a is the root having the same sign as a. So I went through an example earlier, so let's come back here and let's do the square root of 16. An implied index of 2 means it's a square root. Now technically we know there's a plus and a minus answer to this, because if we look for a number that we square to get 16, we have been versed in this, that it could be either a negative 4 squared, which is 16, or a positive 4 squared is 16. So we got our bases covered. But what this statement here is saying, look, if they just want the principal square root, then the principal square root is the same sign as your base or your radicand. So take the square root of 16. If you see that, they're really only looking for 4. Other times they might do the cube root of, let's come back to our 8 again. The principal cube root of 8 is 2. The principal cube root of a negative 8 is a negative 2. I haven't done the negative, so what this is saying is I had to find some number that when I cubed gave me a negative 8. And this is all possible. Because a negative 2 times another negative 2 times another negative 2 is a negative 8. 3 negatives give you a negative. So that's an important concept. So let's run down and look at a few of these examples that they have for us. The first one, the fourth root of 81, in essence, we're looking for a number that we can raise to the fourth power to get 81. Now they're saying it's equal to 3, but we want just the principal square root. Since 81 is positive, all we want is the positive or the principal fourth root of 81. In reality, we know that there's 2 possible solutions here. It could be a plus or minus 3, but as a convention, they're normally just talking about principal square root. and then the rest of those aren't so bad. We want the opposite of the principal fourth root of 81. So we've got a negative 3 there. This one implies, when we're looking at this example at the bottom here, they really would like to have both of the roots. So just some syntax there to try to get us in the right frame of mind on those. Okay, so now let's go through this chart. I'm going to try to simplify this chart with just a few ideas here. Suppose n is some integer greater than 1. Remember, our index n has to be a number greater than 1, but it can't be a fraction or decimal. So it's a nice, neat integer. And a is any real number. We can put anything that we want here, real, and this thing here is an integer. So what if n is even? So I'm going to just write like this. What if we have an even index out here, and a is greater than 0? Well, if a is greater than 0, it has to be positive. If you take the even root of a positive number, such as the square root of 36, we know that there should be one positive and one negative real root. So we have these possibilities of a plus 6 or a minus 6. Therefore, we've been combining these into plus or minus 6. There are two possible roots. And we could also go back to and say, let's look at if it's an even, going down the chart, what if n is even, and now a is negative? That means we're going to be taking an even root of a negative number, such as the square root of a negative 49. There are no real solutions to this. Now, I know we've talked about complex solutions, but they're only referring to real solutions up here. So if we go to the complex solutions, then we would have plus or minus 7i. So we don't have to cover our bases on complex roots in this lesson. And then the final one, as you're going down this chart, if you take the even root of 0, it's always equal to 0. So 0 is pretty easy to work with. Okay, now let's look at the other side of that chart. The other side of that chart says we're going to let the index be odd. Now odd, what happens when we have an odd root of, in the first case, a positive number, such as we've looked at 8 several times, go to 27. Oops, well, first of all, this has to be positive. So here's an example, the cube root of 27. Well, when we have the cube root of 27, there's only one such answer that's going to satisfy this requirement. There's only one number that we can cube to get a positive 27. It happens to be 3, because 3 times 3 times 3 is 27. We don't have an option, there's only one positive. Or if it's the odd root of a negative, where before with an even root it was no real solution, with odds we do have answers. So I'm going to come back and give another numerical example here. So let's do the cube root of 64, but it was supposed to be negative, so I'll replace that with a negative 64. We're really looking for what is the number that we can cube and get a negative 64. Well, if we're going to cube it, anytime it's odd, we know we have to have a negative number in here. So we're looking for a number that is negative. So what negative number can we multiply times itself 3 times to get a negative 64? And that is 4 times 4, which is 16. That's a positive. Then times another negative 4, which would be a negative 64. So they're saying, look, the only answer you can have is one negative. So with odds, you're always guaranteed to have a solution. It's going to be positive if it started positive underneath there. It's going to be a negative root if it starts with a negative underneath the red. With evens, what do we have to worry about? Well, with evens, we have to worry about if it's positive, like this one, then we got 2 answers, where if it was negative, we'd have none. And again, we come back to 0, and 0 has no, or has any root of 0 is still 0. All right, with that being said, let's take a look at some examples here quick and move on. It says evaluate the opposite of the principal square root of 49. Well, since it's the square root of a positive, they're asking for the positive back, but we have a negative sign sitting up front. So it's the opposite of the principal square root of 49 is 7, so it's nothing more than a negative 7. Okay, in example B, they want the cube root of 64/27. So with cube roots, I want to be thinking of perfect cubes. Now, let me just list some squares out here. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, that list goes on and on. Now we want to think of perfect cubes. So perfect cubes would be 1 times 1 times 1, which is 1, 2 times 2 times 2, which is 8, 3 times 3 times 3, which is 27, 4 times 4 times 4, which is 64, 5 times 5 times 5, which is 125, and then 6 times 6 times 6, that list would go on. So we can see from our list here that 64 and 27 are both perfect cubes. So the cube root of 64 is 4, and the cube root of 27 is 3, so it's 4/3. With odd roots, you don't have to worry because it's the same as the sign under your radical, so your radical. And then the final example that I have there is what is the 4th root of 121, negative 121. And this isn't a trick question, it's just supposed to make sure that you're dealing with the real number system only. But if you take an even root of a negative power, you will never get a real answer. So it is not a real number, so there are no real solutions. So we just say no real solutions. We also learned that we could write it as an empty set or a null set. There's nothing there that would work. So that being said, that kind of gets us started with this lesson. I'm going to break this off now.